Hello, now let us see. In this session, we will see the construction of the phase plane trajectory using analytical method. So now we will see what is an analytical, how do we construct using analytical methods. In the analytical method, if you are given a phase plane with x1 and x2 as the phase variables, the idea is to find out the relation between x1 and x2. If you are given the differential equation x double dot plus 2 zeta omega n into x dot plus x omega n squared into x equal to 0, I have x1 dot is equal to x2 and x2 dot is equal to minus 2 zeta omega n into x x2 x2 minus omega n squared into x1. This is a state equation for the system. Okay, so what we do is we find the slopes of the system and then find out a relation between x1 and x2. That means we are getting the time solutions of x1 and x2. If we are having the direct solutions of x1 and x2, there is no difficulty in plotting that in a plane. Okay, so we will see how to get it for a simple equation. Let us consider the simple equation where zeta equal to 0. So we'll see the idea. I will explain the idea using a simple problem, that is when zeta equal to 0 and omega n equal to 1, omega n squared, omega n equal to 1. So we have x double dot plus x equal to 0. So what is the solution of this? So x1 is equal to x1 dot is equal to x2, x2 dot is equal to minus x1. Okay, so this is a state equation for the system. So now we will write down the slopes on the phase plane. We'll try to find out the slope on the phase plane is dx2 by dx1. What is dx2 by dx1? That is minus x1 by x2. Okay, minus x1 by x2. So we will cross multiply this and see x2 dx2 is equal to minus x1 dx1. Okay, we get this relation. So we will try to in order to get the analytical solution, what we have to do, we have to go for integration. Integration is compulsory, otherwise we won't be able to get the solutions for this. Okay, so in order to get the time solutions, we will integrate the equation from x20 to x2. X20 is the initial point and x10 is the initial point for this equation and x1. So I have x2 dx2, and the second right term we will integrate from x10 to x1 of x1 dx1. Okay, so this becomes x2 squared by 2 minus x 20 within the interval. We have to take within the interval. I'm not writing it in detail here, so you can integrate and see those becomes minus x1 squared by 2 plus x10 squared by 2. Okay, so now we can write down this in bring it to one side and write here and cut off all these 2's. We will get it as x1 squared plus x2 squared is nothing but x10 squared plus x20 squared. This is the equation of a circle, right? This, if this is these are the initial conditions of the system. So that is I0 is equal to x10 comma x20. Okay, these are the initial conditions of the system. Now if we give the initial conditions, we have got the radius of the system, right? It is equal to r squared. For example, if it is given as 1 comma 1, that means r is equal to root 2. That means r equals to root 2. So I have the equation of a circle directly. X1 squared plus x2 squared is equal to root 2 squared. So we can directly draw it on the phase plane with this is the initial point 1 comma 1. I have a radius of root 2 here. Since I have a radius of root 2, I can just directly draw the circle here. Yeah, so this is the phase trajectory. This is the idea of analytical method. That means the idea is to find out a relation between x1 and x2. If we get the relation, there is no difficulty in plotting this graph. If you don't know that this is a circle, what you give some value of x1 and find out x2 from this relation, and then plot, find out all those points which matches this, you will get a circle here. So this is the idea of analytical method. Okay. So in this case, the difficulty is like if you are given a nonlinear equation, getting an analytical solution is quite difficult. Suppose, so what we do is we had seen in the previous lecture that about piecewise linear functions. Okay, piecewise linearization. So this was one of the graph that we had discussed there. Something like this. If I have an equation something like this, this is not linear here. It is looking linear. What we do is we divide this into sections. Okay, I have x1, x2, some time functions, time or x functions here. What we do is we divide this into sections, and then what we try to do is we will linearize the function piecewise. Okay, this is a linearized curve. I'll linearize this. Instead of this curve, we will linearize it and write down the equation, linear equation. If we have a linear equation, solving that is not a difficult task. You see? So that is why the analytical method functions well for linear functions. Okay, so we linearize it piecewise, and then we'll try to find out the analytical solutions of the system. So that is about analytical method for construction of phase trajectories. Okay. So now we will go and see a problem where we have a nonlinear element in the system. So this is a problem here. So this is g of s, and this is a nonlinear element here, and it is an ideal relay. So we are switching on and off the system. We are introduced a switch also here. That means we are switching on and off to get some outputs. Okay. So this is, we'll see. So first we have to write down the equation for the whole system. The equation is we have to find out a relation between y and r. Okay. So for that, first we will go from u to y, and then e to u, and then r to y. So first we will write down this equation: u of s ys into s squared ys is equal to u of s. Okay. So that is s squared y of s is equal to u of s. Or can directly write 1 by s squared into u of s is equal to y of s. So s squared y of s is equal to u of s. That means y double dot of t is equal to u of t. So this is the equation between u and y. So I can here itself I will try to choose the state variables. Let x1 is equal to x2, and x2 is equal to, sorry, x1 is equal to y, and x2 is equal to y dot. So we have x1 dot is equal to x2, and x2 dot is equal to u. So this is the state equation with respect to u. Okay, state equation with respect to u. Now we will try to bring in r also, r and e to the system. Okay, so for that what we will do is we will write the relation between e and u. So what is the relation between e and u? When e is positive, the output u is m. When e is negative, the output u is minus m. So I can write the relation here u as u is equal to m for e greater than r, and u equal to minus m for e less than r, and e equal to 0 for e equal to 0. So this is usually represented as by the term u is equal to m sine of e. Sine of e. So sine of e means when e is positive, it is plus m. Sine of e is positive, this term is positive, then e is negative, this term is negative. So this is a general form of representation of this part. Okay. So we will we will be using this equation frequently. Okay. So now what is e here? E is nothing but r minus y, right? So E is r minus y. What is y? Y is equal to x1 here, right? Y is equal to x1. So I can write it as r minus x1 here. So u is nothing but m sine of r minus x1. So I got u also. So we'll plug in that in the state equation. So we have the state equation as x1 dot is equal to x2, and x2 dot is equal to m sine r minus x1. M sine of r minus x1. Okay, now we will go and try to do the analytical method of solution for this. So for that we will write down the slope of the equation dx2 by dx1 is equal to, so that we can cross multiply and then find out the relation. Okay, sine r minus x1 by is it correct? By x2. So I have, we will integrate itself initially itself, x20 to x2 of x2 dx2 equal to integral of x10 to x1. Sorry, we'll cross multiply this m sine r minus x1 into dx. But now we will do this in terms of two equations. So I think I forgot to tell you something. U is equal to m when r is less than x1 is less than r, right? When x1 is less than r, this term is positive. So here we have r x1 less than r. So u is equal to minus m when x1 is greater than r. So that is a relation which comes here. Okay. So we will have to see each term separately to solve this equation. Okay. So we will see each term separately to solve this equation for x1 less than r and x1 greater than r. Okay. So for x1 less than r, what is the equation? Integral x20 to x2 dx2 is equal to integral x10 to x1 m sine r minus x1, right? So m sine r minus x1 means it will be plus m for r less than x. So x1 less than r, it will be plus m. So m dx1. Okay. So for x1 greater than r, it will be, so this we can write it as x2 squared by 2 minus x20 squared by 2. Okay, so if we integrate it, we will get it like this. This will be m x1 squared by 2 minus x1, sorry, this is not x1 squared. Sorry, this is only x1. Otherwise we would have got a circle here, minus x10. Okay, that is the equation. So if we multiply 2 to the other side and find out the relation for x20, we have x20 is equal to 2m x1 plus 2m, here there is also an m here, 2m x10 plus x20 squared. Okay, I think this is minus, right? This is minus. This is minus here. So we got the equation for x20. x20 squared, actually this is, I forgot. I'm forgetting this. Okay, so that is the equation for x1 less than r. This is for x1 less than r. Similarly, we will get for x1 greater than r. So we have the same thing, x20 to x2 dx2 is equal to integral x10 to x1 minus m dx1. Okay, so this becomes x2 squared by 2 minus x20 squared by 2. This becomes equal to minus 2m x1. So here we get a positive here, plus, oh my god, I have put again 2 here, minus m x1 plus m x10. So finally we will get another relation, x20, everywhere I'm making mistakes, I think. This is not x20, this is x2 squared. Okay, x2 squared here, x2 squared is equal to minus 2m x1 plus 2m x10 plus x20 squared. Okay, this is for x1 greater than r. Okay, so we got another relation here. Okay, so we get two equations for the whole system. So we have the relation here because we were trying to find out the relation between, we were trying to find it in parts. Okay, so now here it is very clear. These are the initial conditions we can plug in. This will be known. M is also known. So what is the relation between x1 and x2? The relation between x1 and x2 is a parabolic relation. So it is very clear that we have some r here. The value of r is, let it be somewhere here. R is this line. Okay, this is x1, this is x2. For x1 less than r, I will take this as the region, and x1 greater than r, this is the region. This right side is the region right of r. Okay, so we can see that for x1 less than r, we have x1 is equal to x2 squared positive plus x2 squared plus a constant term here. So depending upon the constant term, we will have different curves. Okay, so this is, in fact, if this is a constant, it is 2m x1 plus a constant. Okay, plus a constant. That means we are going to have curves, we are going to have parabolic curves on the left of the R line. Similarly, we are going to have parabolic curves in the opposite direction in the right, because we are having x1 is equal to minus x2 squared. Okay, it is having the relation of that form, minus x2 squared. So here we have the increasing value of x1 here, x2 here. So this is something we get. The curves will be of this form. This has become, this curves will be of this form. But when it comes at this point, what happens? The curves will be in the opposite direction. It will be something like this. Okay, something like this. Something like this. Okay, so it will be a limit cycle here. So we will get a limit cycle for this. We will plot this in the next sheet. But this is the form of the curves that we get here. Because here to the left of R, we can see a relation which is a parabolic relation. On the right of R also we can see a relation which is a parabolic relation. Because since it is a minus sign, it will be in the opposite direction. Okay. So these points will depend upon the initial conditions that we have. It depends upon the initial conditions. So that is why we are having different curves for different initial conditions. Okay. For now, if you look at the what relay, if we are trying to switch on the relay, this is M and this is minus M. I am trying, suppose I am here, somewhere here. I am having an initial condition somewhere here. I will try to switch on the relay from minus M to plus M at some time t1. We are switching it on at some time t1 from minus M to plus M. So I will jump from this point to this point. So it will be plus M. That means I am having x1 less than r. So I should follow, if I am here, I should follow this curve. I should be following this curve. So I will follow this curve. Okay. So when I come here, and if the switch is put back to minus m, okay, switch off to minus m, what happens that it is going to this part. It is going to this part. That means x1 is greater than r. So if it is here at some time t2, then it will have to follow this curve. Okay, so the working of the relay causes a limit cycle in the system, brings in a limit cycle in the system. So by drawing the phase portrait, it becomes very clear to us that it will be the system is having a limit cycle. Okay, so now we will also see what are the singular points, what are the singular points of the system. So that is also an important part here. So I should have discussed it before starting that the singular points of the system, because what is this value? So how to find out that value? We'll see. So that means the limit cycles will be about the singular point. Okay, singular point will be here at the center. Okay, so we will see what is x1 dot is equal to x2 and x2 dot is equal to m sine of r minus x1. So how will you find out the singular points? We have to find out the time derivatives of the state variables and put it to 0. Okay. So that means dx1 by dt is equal to 0 and dx2 by dt is also equal to 0. Okay. So we will see that dx1 by dt equal to 0 means x1 dot is equal to 0 implies x2 equal to 0, and x2 dot is equal to 0 implies m sine r minus x1 equal to 0. So we also have a relation here, because here we cannot say anything about what is x1. It is quite difficult to say what should be the value of x1 so that the system has to be equal to 0. But we know the equation that we had written initially, x1 dot is equal to x2 and x2 dot, that means y double dot is equal to u. We got that relation, right? Y double dot equal to u. So if you are confused, we will see this equation we got here, y double dot is equal to u. So if we look here, we can see that for x2 dot to be equal to 0, u have to be equal to 0. If u is equal to 0, if u is equal to 0, if you look at this figure, u to be equal to 0 means e should be equal to 0. Okay, if e have to be equal to 0, then r minus y, the difference in r and y should be equal to 0. Okay, so that means r should be equal to y for e equal to be 0. Okay, so now we will go and see that. So this equal to 0, I got x2 dot equal to 0. So this I got it. This is fine. Now we will go and see. This has to be equal to 0. U equal to 0 implies E equal to 0. E equal to 0 implies R minus x1 equal to 0. That is R minus y equal to 0. Right. So R equal to y. Sorry, I should have written R equal to y implies R equal to x. So the equilibrium points are x1 equal to r and x2 equal to 0. So about that r comma 0 point, we will have parabolas. Okay, parabola, we will have a limit cycle. That means it will be something like this. So we will have curves like this. Okay. Oh, so it is not a circle, it will be something like this. Okay, so this is the plot of the curve. So now we will go and plot it using not graphical methods. We'll plot it by putting in the values here, because this is here it is x1 greater than r. I will plot it x2 less than x1 less than r. Okay, this is the x1 axis and this is the x2 axis. So let me choose some values for x1 and x2. So let me choose x1 0 is equal to 4 and x2 0 equal to 2. So I am somewhere here. This is 4 and x2 0 is equal to 2. That means I am somewhere here. Not somewhere, I am here. So here x1 0 is 4 means I will choose r as equal to 4. Okay, r is equal to 4. M as equal to 1. M as equal to 1. So since I am on the upper half, I am here at 4 comma 2. I will be moving towards the right. So I am going to increase x1 greater than r. From left to right, I will be moving. So I'll go and increase x1 greater than r. So this is our r line. Okay. So we have in our mind how the image look like, how the face portrait look like. Our This is our R line, R equal to 4 line. Okay, this is our R line. So now we will plug in for, this is the equation for x1 greater than r, and this is the equation for x1 less than r. So x10 is equal to 4 and 2, and what is the relation? This we have x2 squared is equal to minus 2 into x1. So it is minus 2x1 plus 2 into x10 is 8 plus 4, that is 12, that is minus 2x1 plus 12. So x2 squared, I got it directly. Now I am going to choose different values of x1. Sorry. Now I'll choose x1 as, I'm going to increase it. So let me choose x1 as 5 and 6. Okay. So 5 and x1 is 5. 5 2s are 10, minus 10 plus 2. Minus 10. This is 5 2s are 10 plus 12, which is 2. So we will get it as plus or minus root 2. So we will get it as x2 is equal to plus or minus root 2, or x1 is equal to 5 here. We'll get definitely two values here because since it is a parabola. But now we are on the positive side, we'll choose it as plus root 2. So it will be plus root 2 here. And when x1 is equal to 6, what will be the value? X2 will be equal to 0. So you can plug in and see it will be 0. Now again, when we are here, we know since it is a parabola, we are going to decrease it. So we will choose this 5. It will be minus root 2. And then again go back to 4. It will be 2. Okay. So you can try out these values. So I'm going to do here. It is 1.414, some point somewhere here. Sorry, for 5 I have. For 5 I will be somewhere here. For 6 I will be here. For again for 5 I will be somewhere here. For 6 I will be at 2. 1 and 2. So we have a curve here which is a parabola. See, this is a parabola. I got a curve which is a parabola. I'm moving from this point to this point. Now when I reach here, what happens? I have to, here I have x1 greater than r. So I am here at 4. This is minus 2, sorry. This is minus 2. So I am at 4 minus 2. Now I have to decrease the value of x1. So we go to 3. We go to 3. What is here? When it is 4, here we have x10 and x20 as these values here. So we have x2 squared is equal to 2x1 minus 2m, 2x10 is equal to minus 8 plus 4. So this becomes 2x1 minus 4. Okay. So this x1 is equal to 3 means I get here 2. 2. X2 squared is equal to 2. So I have x2 is equal to plus or minus root 2 for x1 is equal to 3. So since I am at minus 2, I will go to I will choose minus root 2. So I will be here minus root 2. Then I'll go and choose 2. X1 is equal to 2. Some values. You can also choose values in between, only chosen with step size 1. Okay, so this becomes 0. Then I'll go to again 3, I will get plus root 2, again 4, I will get 2. So I have got all the values here. So I'll be somewhere here, I'll be here, I will be somewhere in this similar to this point here. Okay, I have to be here. So I got the values for x1 less than r also. See. So this is for x1 less than r. So we can plot the lines. Okay. So you can see that if you are here, somewhere here, and we switch it on from the, you will be here somewhere here when you will be, when you can, when the switch is on. And when you try to switch it off, we go to minus m. So we will follow this path. So we have a limit cycle. When you try to switch it on, we will follow this path. Okay. So that is the situation. So this point is the equilibrium point, 4 comma 0, because r is equal to 4. This is the equilibrium point. So we can draw infinite number of curves depending upon the initial condition. So I'll give you a chance to draw these curves now. See, I have given you a question here, so you can also draw some curves. Okay, so this is the question that you have to do. Okay, for I have given the same problem here, but for different values of r equal to 3, and x10 is equal to 3 and x20 equal to 3. So first curve you will get. Then for different initial condition, I have changed x1, x20. You should draw another curve. That's it. So you will get different curves on the x1, x2 plane. So this is about plotting the curves, but the total idea of this session was to find out a relation between x1 and x2. If you have a relation between x1 and x2, even if you are not plotting the exact values, you will get the system response, how it looks like, whether there is a limit cycle for the system, whether it is oscillatory, whether it is damping, and whether it is stable or not. These kinds of relations you can get from these equations. Okay, this is the equation. This is the first equation that you get. This is the second equation. So the idea is to find out these equations directly. So this is the time equations between x1 and x2, relations between x1 and x2. So this is about the analytical method. Now, this sometimes becomes tedious to find out the relation. So we usually go for graphical methods of plotting the phase trajectory. So we will see that in the coming two lectures. One is the isocline method and the other one is delta method. Okay. Thank you.